So when we get started, let's just talk a little bit about what quadrupeds are. Right now, this is Big Dog. It's one of probably the most widely known quadruped out there. Focuses highly on stability. It's out there for the military. As you can see coming up, right here is a new quadruped that's based on gait design. It's out at the Chinese Institute of Technology, and they're starting to pop up everywhere. So who are we? So we consist of a team of Vadim Cherniak, Timothy Flynn, John Morgan, Jeffrey O'Rourke, and Anton Zalewski. We'd also like to acknowledge our advisors, Dr. Sonia Chernova, Dr. Stephen Essinger, and Dr. Taskin Piquet. So what are some of the project goals for this? So we aim to develop a base for further legged locomotion research. And with that, we really want to try to recover and monitor energy loss with each step, as well as develop a compliant spring system capable of reproducing slip, which is a series-loaded inverted pendulum model. Again, using that system, we like to achieve a statically stable 5 feet per second walking gait, which once we have that, we also want to be able to sense the surroundings using an IMU, a LiDAR, and a camera, specifically focusing on staircase recognition. Going outside of that, we want to try to use an A-star algorithm to develop some path planning, and with all that together, we'd like to explore more dynamic gaits, including some trotting and running. So, what are some of the applications for this? As you can see right here, this is a boulder field. It's very acceptable to interact with this as a robot in the field. And usually, wheeled robots can't cover 70% of land mass on the world, but legged robots can explore out into that. And while they're doing that, they can carry heavier loads. Here you see the iRobot Warrior with an APOP system on top of it, which weighs about 80 pounds, but it wouldn't be able to get through that boulder field previously. Also, if any tracked robot can get through difficult terrain, they go through it very, very slowly. As you can see here, the Jeep can get up that hill, but it's going to take it quite a while. Reaching outside of just going through difficult terrain, we also aim to add a level of mechanical compliance so that we don't have to focus on large software restrictions. So what were some of the inspiration for this? Obviously, Big Dog. Big Dog also has a brother project, Little Dog, which is a research project. Another thing is the Raver Hopper, which actually reproduces that slip model and is able to balance on that like a pogo stick. Moving on, there's the Spring Flamingo, which uses series elastic actuators to reproduce, again, similar slip model. Current project with Carnegie Mellon and the University of Michigan is Mabel, again, building off of the Spring Flamingo, as well as the Achilles project, which aims to reproduce what tendons are in your legs. So, this is a current CAD model of our system.
So meet Sabertooth. Just to put it in perspective, it's about 3 feet tall. See, it's next to a human. Each leg has 3 degrees of freedom. So it's got the shoulder, knee, and then a hip for camber. We designed it to be capable of carrying a 30-pound payload about the size of a cinder block. And the legs are completely cable driven. So it also has a 2 degree of freedom passive center body joint that acts like a spine between 2 body sections. And just like some more dimensions, it's about 3 feet, 3 feet wide. Weighs about 300 pounds. So it's a quite a large system. So here you can see there's the cable system that goes down from those upper teardrop shaped drive pods down to the legs. And then you can also see the center body section in between the center body joint between the 2 body frames. So let's go through the mechanical design process that we went through. So we modeled the entire robot as you just saw in SolidWorks. So we would develop the CAD model for what we wanted. And then we would turn to our analysis tools. So finite elements analysis using ANSYS. And we would go into ANSYS, we would put some of our most critical parts in a worst case scenario. And then using that information, we were able to go back and redesign. And then after we redesigned, we would go and make full-scale prototypes. So another example, this is the body joint again. This is a full-scale prototype using acrylic and wood. So obviously this wouldn't take the whole, anywhere near the actual weight of the real one would. But it allowed us to study the motion of it because it was a fairly complicated part that we wanted to be able to study the range of motion of it before we built the full-scale model. And then we moved on to final assembly of the actual part cut out of metal. So we did this prototyping method for a number of systems. So you can see in this video, this is the body joint twisting back and forth. That's one of the degrees of freedom. And we also built an entire full-scale model of the leg using MDF board and acrylic to test not only the spring system, but also to check clearances and check cable routing one last time before we cut the actual parts. Here you can see this is our linear actuator for the camber of the legs, it's using like a lead screw. And we also applied this not only to the mechanical portions, but to the entire system. We set up test beds for the entire electrical and control system as well. You can see we have this, this is a CAN network of 4 Maxon motor controllers operating linear actuators.
All right, so how are all these parts made? Unfortunately, this doesn't come in a kit. Okay, so going down. Luckily at this school we have a Haas Technical Educational Center, and we use it to its full capabilities. Here you can see some pictures of us putting the side plates in the VF4. Here's one of the setups that we have for the pulleys. Sorry, my throat's down. The unique thing about the pulley is that we actually use the live tooling on the lathes, which is very unique. I think it's one of the first times anyone's actually ever done that. And it was because of that reason that we were able to basically mass produce them. We had to make 40 total pulleys. Here's a picture of some welding, picture of some more milling, picture of some sparks, because everyone loves sparks. I have that picture in there. And the one thing that we did actually outsource is we had a few water jet parts which we sent out to one of our sponsors. So this is about it, the stuff that we didn't make ourselves. Oh, and some more pulleys, just to give you guys perspective of how many there were, and some of the blanks that we had to start with. And here they are actually done. Yeah, looking out pretty.
So what's so unique about this robot? Why is this special? And what we have is called the spring-loaded inverted pendulum. So I'm trying to explain this. Imagine your leg's a pogo stick, and as you walk, you compress the pogo stick, and then it pushes back. And that's pretty much a breakdown of what the spring-loaded inverted pendulum is. And as I apply it to myself, as you apply it to yourself, it also applies to other animals in nature. Maybe a chicken or a dog, as it comes to this model right here. And again, here's another great example of how that is a fluid motion, that compression and then explosion off the ground. That's how runners get so much power. So how did we recreate that in our system? So through research, we know to understand that our tooling system has a lot of forces going through the rotary joints. And by applying springs to the rotary joints, we're able to make an equivalent linear system, as you can see on the right. So through our cable system, this is an image of a cutout from our shoulders. So each shoulder has 2 spring systems, one for the knee and one for the shoulder. And the way they work is the knee motor goes to an idler pulley, and the idler pulley is connected to the joint. And between the idler pulley and the joint, on one side we have a spring, and on the other side we have a tensioner. And as the leg hits the ground, it will pull on the spring, putting slack on the other side of the cable, so the tension will pull it up. And that was how we are able to capture that force. We also looked into nature and were able to create a passive both front and back angles based off of the anatomy of like a lion or a dog to show how that is able to have a dampening force from the gas spring in front as well as the springs in the back. Why would we do all this? Well, this allows for a high order of mechanical compliance as well as the ability to step on unpredictable terrain and while completing walking gaits in a very normal fashion without a lot of competing. How did we do this?
So, did we guess? The logical answer is we're not that lucky. So we used TH parameters using rotational transformation matrices to express it in a Cartesian coordinate system, and you can see how our robot looks. This is actually our robot model with that. Now, inverse kinematics, what we want to do is we want to go using these equations here. What we want to do is we want to go from an initial XYZ position, we want to go to a secondary XYZ position. How do we get there? Well, we have to bend the angle somehow. These equations right here do that. Gait calculations. So what we do, what's a gait? Think of an animal running, or an animal trotting, an animal walking. That's what a gait is. We use gaits. These duty cycles here show how much, the black shows the allotted time of the ground, where the white represents how much time is spent on the air. Here you can see different types of gaits that we've actually implemented in our system and in our simulation.